Last week we left off, I did this kind of group of definitions for you. We walked through and discussed there should be a P there, how we define potential and potential energy. And I did it for you in terms of units. Now I want to kind of reinforce that because I'm going to take us a little bit back to 161 stuff and then bring us back forward and help you kind of come to terms with the signs on things and where they magically come from. So first of all, remember we talked about force acting on a charge being in terms of, let's see, we'll call Q1 the source charge, so the charge creating the electric field. And then the distance away, in this particular case, instead of the distance away we're measuring the field, this would be like the distance away that Q2 is interacting with that net electric field. And to kind of bring you back some, and the quiz I gave you week before last, I had these two positive charges at this same distance from this point. Remember the point, the little probe charge we consider as a teeny, 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 tiny positive charge. And we determined the electric field at that point. And then we looked at this and we said, okay, so KQ over R squared, let me write, I don't want to mess this up. Let's go with our electric field as just KQ over R squared. And the Q was taken one at a time. So we looked at the net electric field vector from Q1, and we said, okay, so it would be coming out this way because fields emanate out from positives and into negatives. That's how we've defined it. And the same for Q2, coming out of it and then pointing out this way. And then one of the things I was able to talk with a lot of you about is the way to think about this is this KQ over R squared. Well, that's just the hypotenuse. So that's like the resultant electric field. And when we want to add these things, I can't just add resultants together. I have to do it by components. And the reason why for that is that when I look at this thing, I'm the same distance away from both, same magnitude of charge. So both of them have the same resultant. And same distance means that the same angles. So their x and y components were identical. And then we looked here and we said, okay, so this piece coming down here would be like the y component for E1. And this piece here, let's do a different color, would be like the y component of E2. Because they're equal and opposite, they cancel out. So the resultant net electric field then was this piece here. And so we said, okay, if I bring a positive charge and put it at this point, it would go in the direction of that net electric field. And why? Because we've defined fields as going out of positives and into negatives. So if they're coming out of a positive and going into a negative, then this thing, essentially you can think of it as pointing towards a negative charge, if you will. So a positive would be attracted. The other way to think about it in terms of forces, I have these two positive charges in the top right and bottom corners. It's repelled away. In terms of potential, if you remember this thing here, I talked about that being a capacitor. So two plates, one's positively charged, one's negatively charged. And the thing I did last week is I talked about that the fields between this are constant. And you can kind of think about it as I'm going to have an equal amount of positive charge as I have of negative charge. And because charges will equally distribute themselves so as to minimize repulsion, then I'm going to have like this kind of straight line action happening from one to the other as far as my field lines go. I'm going to have coming straight out of a positive right into a negative. And that's going to go all the way down. So I'm going to have this whole collection of field lines going on here. Kind of taking this, and there's a reason why I started off with our quiz question from last week, taking this in terms of our potential, then what's happening here? Well, what we say, how we define this is standing on the top of the high board. So I have high potential on this side. High potential. On this side I have low potential, or no potential, if you will. Another way to look at that is like if this was like a battery, I could think of this in terms of I have 10 volts here and no volts here. So if my positive charge is experiencing this field, it's going to start from a place of high potential and go to low potential. It is moving in the direction of the field. It is losing potential. Where's that potential going? Well, that's going into speeding up the darn charge, right? Just like jumping off of the diving board. I start off with high potential energy. I end up with no potential energy when I consider the water my zero line. And that means that all of that potential is converted into kinetic. So let's go back to our units then, because now we can think of this in terms of potential. So this would be high potential, capital V, capital V. Looking back at our units, we define then the force as being the electric field acting on a charge. And I can look at this in terms of the units. This is, let's see, I can rewrite this. Actually, I'm going to take this little thing out. I can rewrite this if I want, and then say I can define the electric field as being moving the Q to the other side, force per charge, per coulomb, or newtons per coulomb. You'll see that's what I have this labeled as. So my electric field is the amount of force that can be exerted per coulomb of charge that experiences that field. That's the other way to think about it. And then I can come over here, and remember we went through the units of potential, not potential energy. And we said, well, potential, the V, has this units of joules per coulomb. So the amount of energy available per coulomb of charge that's going to experience that potential, or the potential difference. And then we can write that, we're like, so this is newtons per coulomb here. Ooh, newtons per coulomb. Well, E is newtons per coulomb. So I guess the other way we could look at this is to say that this would be what? E, the electric field, times some distance. Here's my electric field, my newtons per coulomb. And this is the distance that is going to be. That is also a different way of looking at V. Now, the one thing I didn't say last week is, while I'm giving you the fundamental units that go in there, you're going to like this. The units of voltage, or volt, is V. So potential, electric potential, has the symbol of V and the units of V. And I don't know if that makes life easier or a little bit more confusing, but they're both going to be the same, at least look the same. So potential energy then is taking my potential, my V, and multiplying it by Q, because if I do that, what happens? If I multiply it by Q, that C goes away. I have units specifically in terms of energy. So now why do I have these graphs? Let's look down at the graphs. In 161, we would do force versus distance graphs. And we looked at those and we said, let's see, what's the slope of that thing, rise over run, force per meter. I don't know that really helps me much. But then I can look here and say, what is this? This would be the integral of force. Gives me the area under the curve, which is what? That'd be like, for this thing, would be like a spring. 1/2 base times height, so 1/2 force times a distance. The other way to look at that is that gives me newtons, meters, otherwise known as joules. And we related that to work and energy, same thing. Okay, now let's do the same thing with our electric field. If I plot an electric field, and I have this kind of odd graph going like this, and I don't know, we can give 1, 2, 3, it doesn't much matter. We have our units. If I want to do the same thing, so I'm going to integrate the area under the curve of an electric field. What do I get? I get 1/2 for this, just because I chose this particular shape. 1/2 base times height. So newtons per coulomb times meter. Okay, so what is that? Newtons per Coulomb times meter. Woo, that gives me potential. This gives me V. So it's not quite what we're looking for. Not quite. If we want energy. But if I want to integrate the electric field, then my KQ over R squared, if I integrate this with respect to R, what do I get? Well, the KQ would come out because it's positive. And then I have this R to the negative 2. So remember, we're going to add 2 for an integral. You take away from when it's a derivative. So I'm adding 2. So to give me R to the negative 1, so I'd have KQ times, I got to pull the negative 1 out because remember the rule of integration. Oops, I don't want this anymore. The rule of integration is that when I take the derivative of whatever I come up with, it had better be the original equation, which is this guy. So 1 over R. So another way to think of that, R to the negative 1, if I take the derivative and take 1 away, I pull the negative 1 down, right? And that's going to make that negative sign go away, and I end up with the R squared, so I get the same thing. And then evaluate it from 0 to x or wherever we're going. This looks a lot like our potential equation, but there's a negative sign in there. So where is the negative sign coming from, and when do you worry about it? And that's a big reason that I wanted to have this conversation. And that is to say the same thing I said in 161, and the same reason that I've really kind of tried to get you to focus on looking at the directions of fields and forces and how things are going to interact, and then decide for yourself, is my potential increasing or is it decreasing? What your book does with this is it says, well, we'll pull the negative out and we'll just flip this and we'll go KQ over R if I'm looking at a delta V, which is what that would give me. And my R, my delta R here, is going to be KQ, and what they say is R initial minus R final. That's why that positive sign stays there. So I'm getting the same quantity. The question here is, do you get buried in the frustration of, am I going to lose a negative sign here or not? Or can you just kind of think it through? And that's why I started with my fields. So my fields go from a high potential to a low potential. They point towards the negative sign from a positive charge. So if I bring a positive charge into that field direction, if I brought in a little positive charge here, I would say that it has a high potential and it's going to a low potential. So its overall change in potential would be negative. It's losing potential. If I bring my positive charge here and want to bring it out this way, my potential is increasing. The overall change in my potential is increasing. So when you're going through things and trying to decide, is something a positive or a negative, just ask yourself. And we've done enough with the electric fields now that you can quickly draw out some vectors and kind of overall ascertain what direction the net field is. And that will help you figure out what your positives and negatives are. I'm trying to decide if I want to turn this also into energy, but I think this is a good place to stop, and we'll do a practice problem here next.